A binary relation is a set of ordered pairs that shows the relationship between elements of two sets. This concept is primarily concerned with the association of one element with another, say a mother and child, a boy and a girl, green and blue, ordered pairs based on how we define them. Now from the example we have here, we have R as our binary relation, and the elements of the binary relation are this ordered pair. Note that you don't have to worry about the meaning which a given ordered pair conveys. That means the relationship between A and fan, you don't have to bother the meaning is conveyed. It is just an ordered pair based on how we define them in this case. Now this is an ordered pair of number. We don't have to bother about the rule of which A and 2 form an ordered pair. What we just know is that they are ordered pairs based on how we define them. So from this, we observe that the ordered pairs form the foundation of a binary relation. Now, what is an ordered pair? Given two objects X and Y, if you have a set, let's say set A, which is formed from this object X and Y, if this set X and Y is the same thing as set B, Y, X, so you see that the order of arrangement does not matter. So these are sets of what? Unordered pairs. Because we say that this set A is same thing as set B, that means they are equal. If it becomes necessary that the order of set matters, like we will see in special examples, in that case we now talk about another pair. Now using this same object, now if you have another set C, which we define as this X, Y, we see that this is a set of ordered pairs because this is not equal to set D, which we define as Y, X. These two sets are different, while these two sets are the same. This is a set of what? Unordered pairs, whereas these two are sets of ordered pairs. That means this is not equal to this except X is equal to Y and Y is equal to X. This first element of this ordered pair is called the first coordinate, while Y, the second element, is called the second coordinate. So this is an ordered pair. We can even proceed further to have an ordered triple. For example, if you have another set E, which we denote as X, Y, Z, this way, this can form an ordered triple. We can also proceed further to define set F, which we call an ordered quadruple. Y, Z, let's say V. This is an ordered coordinate. That means the order of arrangement matters. This is the first coordinate, second coordinate, third coordinate, fourth coordinate. So now we proceed to a very important application of the ordered pair, which we call the Cartesian product. And here we see that given set A and B, the set consisting of all the ordered pairs U and V, such that U is an element of A. That means trying to specify the order now. And V is an element of B. Is called the Cartesian product of A and B, denoted and is denoted by A cross B. So this is the Cartesian product definition. Now what this is trying to tell us is that if you have a set A, let's say this set is A, B, C. This is a set, right? I'll have a set B, which we call 1, 2. Now what this Cartesian product is telling us that the crossing of these two will form a set of ordered pairs, which the first element, which is called the first coordinate, is A, while the second element, which is the second coordinate, is B. Now in this case, if we say A cross B, this crossing will give us a set of ordered pairs from definition. So this crossing will result to sets of ordered pairs. Here we have A, 1. Remember, the order of arrangement of this element matter. You have A, 2. Then next we have B, 1, B, 2. Then we have C, 1, C, 2. So the Cartesian product of these two sets gives us a set of ordered pairs, which is this. It has 6 elements. If you check, the element of this is 3, the element of this is 2. 3 times 2 is what? 6. So the crossing of A and B will give us a set of ordered pairs that have a set of 6 ordered pairs. In a test or an exam, a question may be posed giving this set A as this and B as this, that which of the following is a member of the set. Now if there happens to be an option that says 1 comma b. This is not a member of this. This is not an element of A cross B. Why? Because the order of arrangement matters. 1 comma b is different from b comma 1 because this is an ordered pair. I want you to get this definition very well. This is different from this. So this is not an element of this cross product, that is this Cartesian product. It's not an element. So this is the odd member. Whereas 1 comma b is an element of A cross B. So this one is this. Since it's another pair, is different from. So from this, we see that the language of set is aimed at facilitating our understanding of associating one element with another. So now let's look at another example of this Cartesian product. So if we are to show the Cartesian product of W and Y, W cross Y will give us the set of ordered pairs this is the Cartesian product of W and Y. Now if you observe, you see that this is a binary relation. So clearly we can say that a binary relation is a subset of a Cartesian product. That means the binary relation of two sets A and B is a subset of the Cartesian product between A and B. So that's just the basic definition of what binary relation entails. If a binary relation is a subset of a Cartesian product, the empty set, is it a binary relation? Put your answer in the comment below. So next we delve into the domain and range of a relation, that is a binary relation. I will say that given a relation R, the set of first coordinates of the members of R is called the domain of R and is denoted by dom R, while the set of second coordinates of the members of R is called the range of R and denoted by range R. So if you have, this means that if you have a binary relation R, which we define as this, this is a binary relation like we have seen. Now the domain of this binary relation denoted by dom, domain of the relation R, is a set of the first entry. So when we bring the first entries together of this binary relation, we get the domain of R, and clearly we see that this is A, B, C. Remember, in sets, repetition is not ideal. So this is the domain. Then the range of R. The range is the what? The set of second coordinates of the members of R. So the second coordinate in this case is what? So this is the range of the relation, while this is the domain of the relation. Here we have another example of a binary relation which we call the relation D. And in this case we define it with just numbers. And now if you look closely, you see that the domain, so you can solve it and put the answer in the comment below even as we solve. The domain of D is the set 2, 3, 8. While the range of D is the set 5, 7. Remember, no repetition. If you observe from this case now, see that the first entries we have here are unique, unlike the previous one where we have letter A as the first entry of two ordered pairs. Now in this case, the first entries are unique. Now this points us towards a special kind of relation which we call a function. Now a function is a special kind of relation, just like this one, where no two elements of the binary relation have the same first entry. If you observe, no two elements of this our binary relation have the same first entry, and that special kind of relation is what we call a function. Now in this video here, we talked more on the function, the different type of function, and how function is the foundation of different mathematical concepts. So we'll see you in the next video where we talk more on function. Thank you. Please subscribe.